Okay, so in the last video we talked about centripetal force, centripetal acceleration, and in this video we are going to talk about centripetal force. But before we get to that, I want to talk about a type of problem that you see throughout IB physics, and this might be the first time we've seen this specific type of problem, but this type of problem shows up in all kinds of different units. And this is what we call a proportional reasoning problem. And basically the structure of this type of problem is the question asks you, how does one variable change if another variable or multiple variables change in some specific way? Okay, so this particular question, this is example 4. This says a ball being swung in a circular path of radius r and velocity v has a centripetal acceleration ac. Now I will just note, by the way, we know the equation for centripetal acceleration, that is v squared over r. Now the question says determine in terms of AC. Anytime you ever see a problem say in terms of, that means your answer should be a multiple number of that thing. Okay, so in other words, the answer to this question is going to be a multiple of AC. It says determine in terms of AC the centripetal acceleration the ball would require if its velocity was tripled. Okay, so in other words, we know from the equation that if we increase v, we're going to increase the centripetal acceleration. That much is obvious just looking at the equation, because obviously if you multiply by a bigger number, you get a bigger number. Okay, but this question wants you to be more specific. If we triple v, by how much, by what factor does AC increase? Okay, so this is basically what a proportional reasoning question looks like. Now there's two ways to approach this question. I prefer a more generic algebraic approach. And so here is how I like to approach this type of problem. I'm basically looking for what I'm going to call AC prime. I'm looking for the new centripetal acceleration if I make the changes they want me to make. And in this case, they want me to make the change going from V to 3V. Okay, they want me to triple the velocity of the object. Okay, and so for my new centripetal acceleration, which I'm going to call AC prime, this dash means prime, I'm going to make that substitution. So that means instead of v squared, it's going to be 3v squared. That's very, very, very important that the 3v go inside the parentheses, okay, because it's not v being squared, it's 3v, the entire thing, 3 times v, all of that is now being squared. And then divide by the radius, which stays the same. Now, if you do that, 3 squared is 9, and then v squared is v squared. And so my objective is to find AC prime is equal to some number times the original AC, because the question says determine in terms of AC what the answer is. Okay, and so what I'm going to do now is just compare my original centripetal acceleration to my new centripetal acceleration. And just by inspection, you should be able to see the difference right away. They're basically the same equation, except my new centripetal acceleration has a 9 in front of it. In other words, by tripling the velocity, I don't triple the centripetal acceleration. I actually increase the centripetal acceleration by a factor of 9. Okay, and if I were to double v, then that would quadruple the centripetal acceleration because 2 squared is 4. And so this type of proportional reasoning question shows up in a bunch of other different units throughout IB physics. And really, it's not really a physics thing. It's actually really a math question, just kind of using physics equations to go along with it. Okay, so again, this type of question asks you, how does this one thing change if this other thing changes? And this is common to see as multiple choice questions on the IB exam, where like the answer choices might be like, 3 times AC or 9 times AC, which is the correct answer, or, 1/3 times AC. Okay, and so this is a very common type of multiple choice question. All right, so let's move on and get to centripetal force. Now, just to recap, in the last video, we talked about how objects moving in circular motion, because their direction is changing, their velocity is changing. And if their velocity is changing, they must be accelerating because of how acceleration is defined. Now, in this class, we're mainly going to be focusing on what's called uniform circular motion, which is a situation where the angular velocity of an object is constant. Okay, and we know that an object moving in circular motion has a centripetal acceleration, which is directed towards the center of the circle, that is directed radially inward. We know it also has a tangential velocity. The linear velocity of that object would be tangent to the circle at every point in space, and we know that that is given by the equation AC equals v squared over r, or in terms of angular velocity, r times omega squared. Okay, we talked about that in the last video. Now, going back to Newton's laws of motion, it follows that in order for an object to accelerate, what is necessary is a net force. Okay, right? Net force is equal to mass times acceleration. That's the old Killer Bunny equation. That means in order for an object to experience any type of acceleration, there must be a net force acting. All right, and so we've talked about the acceleration aspect, the centripetal acceleration, but now let's talk about that net force. Okay, so this again goes back to Newton's second law. We know F net equals ma, but in the context of circular motion, sorry, I'm trying to adjust the size here. In the context of circular motion, the a is not just any old a, it is centripetal acceleration. And so if you think, okay, F net equals ma, what if we have circular motion where the acceleration is centripetal acceleration? In that context, we call that net force something different. Okay, we could just keep calling it F net, but we don't. In the context of circular motion, we switch to calling this net force centripetal force. Okay, so F net becomes Fc, and Fc, net force, is just mass times acceleration. And so that would just be m times v squared over r. Or if you prefer, m times r omega squared. Now, Fc, the reason it's called centripetal force is because the direction of this force is also towards the center of the circle. Remember, centripetal means center seeking. Okay, and so the centripetal force is the net force acting on an object in the radial direction. Okay, so rather than, F net x is the sum of the x forces, F net y is the sum of the y forces, F net c, you could call it this, but people don't. F net c you can think of as F net radial. Okay, the sum of the forces in the radial direction. Nobody would ever call it that, but that is what it is. Okay, it is a net force, which means it's not like, tension or gravity or friction or something like that. It is provided by one or more other forces. Okay, so the net force in the radial direction is what we call centripetal force. Okay, so pause there and make sure you add that to your notes. Okay, so I said this before, but the centripetal force has to be provided by one or more forces acting in the radial direction. So that could be gravity, that could be normal force, that could be friction, tension, depending on the context of the situation. But it is the sum of the forces acting in the radial direction, which means if I have a situation with two radial forces, then I would do the sum of the forces. Okay, by convention, radially inward, the radial inward direction is taken to be positive. Okay, up, down, left, right, none of that matters. If it is going in towards the center of the circle, you take that direction to be positive in circular motion, and radially outward is taken to be the negative direction, always. And so basically what we have here is we have an extension of a second law problem, because we still are going to have things like free body diagrams and, some of the forces and all that stuff. Okay, that's why this unit is an extension of mechanics. Okay, so take into account what I said about the radial inward direction is always taken to be positive. If it is not a radial force at all, then it has nothing to do with centripetal force, and you treat it just like we did like last semester. Okay, and so we're going to start off with a very basic example. And so here we have a tether ball. Okay, and hopefully you played tetherball as a child. And if not, you can go to YouTube and find a tetherball clip, like, in 5 seconds. But basically, tetherball is the game where you have like a metal pole and a ball is attached to a string, and they have them on playgrounds, and you hit the ball, and the string, goes around the pole, etc. Kids play it. It's a fun game. Okay, so this is a ball attached to a pole by a string, but notice that the string is actually making the ball move in a circle, and the string itself is at an angle. Okay. The question says, in the game of tetherball, the struck ball whirls around a pole. In what direction does the net force on the ball point? Now, as I'm looking at this question, I'm thinking two things. Number one, there's only two forces acting on the ball, and they put W and T because the IB uses that notation. We think of this, of course, as Fg, the force of gravity, and Ft, the force of tension. Okay, I don't like the W and T notation that the IB uses, but that's what they use. There's two forces acting on the ball. Why is there a net force on the ball at all? How do we know that the ball is accelerating? Well, if it's moving in any type of circular motion, it has to be accelerating. It has to have a centripetal acceleration. And so there has to be a net force. There has to be a centripetal force acting on the ball. What is the direction of the net force? Well, the centripetal force goes towards the center. Okay, so I'm thinking, okay, Fc equals mv squared over r. And going back to second law problems, we know that what you do is after you do the right side of the equation, you write down the sum of the forces. So let's think, what forces are acting in the radial direction? Because remember, centripetal force is the sum of the radial forces. All right, radial means in towards the center and out from the center. Now looking at the FBD that they give you, there's no forces going out from the center. Tension is not going towards the center of the circle because here's the center, but a component of the tension is. Because if this is Ft, then part of Ft, this part right here, that would be Ftx, is going towards the center of the circle. So what does the sum of the forces look like? You would just put Ftx. The question is just a multiple choice question. In what direction does the net force on the ball point? That would be along the horizontal component of the tension force. And the answer would be C. Now, what about Fty and Fg? Well, Fty and Fg you do just like normal. You would do like F net y equals may. The ball is not accelerating up and down, it's just accelerating in a circle. And so you just have Fty balancing out Fg. Okay, nothing exciting there. We've done that type of problem like a million times before. Okay, the new piece is in the x direction because of the circular motion. And then if we had numbers here, we could plug in the numbers. Okay, so pause there and make sure you understand example 0.5. And then this is just like the solution to that. Okay, now example 1. Again, we're going to start with a very basic circular motion question. So example 1 says a ball with a mass of 0.2 kilograms. Okay, so I have mass on a string is swung in a horizontal circle. The circle has a radius of 0.5 meters, and the tension in the string is 5 newtons. So that's Ft. Now we're asked to draw an FBD based off of the picture. I'm just going to draw it on the picture because it's easier. I have the force of gravity going down, and then there is tension in the string going towards the person's hand. So Ft is going to go that way. Notice, by the way, that the question refers to a horizontal circle. It's really important that you understand the difference between a horizontal circle and a vertical circle. What's shown in the picture is a horizontal circle because the plane of the circle is horizontal. A vertical circle is where you're swinging something and it's going like up and down in a circle. Okay, so in a horizontal circle, the FBD looks like this. You got gravity going down, tension going towards a person's hand, which that's where the center of the circle is the person's hand. Now the second question says, identify which force or forces are providing the centripetal force. Well, the centripetal force is the net force in the radial direction. Which of these two forces are radial? Well, the only force going towards the center of the circle is tension, so the answer to the question is just tension. Gravity does not play any role in the centripetal force in this problem because it's going straight down. It's not going towards the center of the circle at all. Okay, and so for calculation purposes, I would just do Fc equals mv squared over r. This, by the way, is basically Newton's second law. It's written in a different form, but this is basically Newton's second law. Okay, F naught equals ma is now Fc equals mv squared over r. I write down the sum of the forces before I plug in any numbers. So I've got my FBD. I do know the mass, by the way, is 0.2. I know that V is unknown, so that's going to be V squared. And I know the radius is 0.5. And now that I have the sum of the forces, I can plug in for Ft. So that's going to be 5 equals 0.2 times V squared divided by 0.5. And so if you rearrange this and, do some algebra, that's pretty basic algebra. We're going to get a number for V, let's say 5 times 0.5 divided by 0.2, take the square root, we get 3.54 meters per second. I put 2 decimals just because I felt like it. Okay, so that is how fast the ball is moving. Okay, again, simple calculation with centripetal force. Pause there if you need to look at it some more. Right, let's just do a couple more examples. Okay, so example 2 is a very similar looking example, but now it says a ball with a mass of 0.2 kilograms on a string is swung in a vertical circle. And it says that the circle has a radius of 0.5 meters and the tension in the string is 5 newtons. So the only word that's changed is now instead of horizontal, it says vertical. Now, I need to make a quick modification really quickly. I'm going to say the tension in the string at the bottom of the circle is 5 newtons. And the reason I have to put that now, I have to qualify my statement, is because actually the tension in the string is going to change when you swing the ball around in a vertical circle. It's actually going to be bigger at the bottom than it is at the top. Okay, and so here's how that works. Here is the string, and let's say here is the ball at the bottom of the string, and forgive my bad drawing, but let's say the circle is something like this. Okay, so I'm swinging it around this way. What does the FBD for this look like? Well, I know I've got gravity going down, not a surprise. Now here's a slight conceptual thing that's really important that you get. There's two forces on the ball. There's gravity and there's tension, right? Tension is going along the string towards a person's hand, so tension clearly has to be going up. But the force of tension has to be drawn longer than the force of gravity. Okay? Ft is bigger than Fg. Now, how do I know that? Well, because the centripetal force, by definition, goes towards the center of the circle. Okay, that means the net force, when you add up the sum of the forces in the radial direction, has to be going towards the center of the circle. That means the forces towards the center always have to be stronger than the forces going away from the center. Okay, so Ft has to be bigger than Fg, otherwise this situation isn't even possible. Okay, so there is a net force. The arrows are not the same length, because then the net force would be 0, which is not possible. Ft has to be bigger than Fg in this case. So I have my FBD. It says identify which force or forces are providing the centripetal force. So I think, okay, which of these forces are radial? Well, in a vertical circle, these are both radial forces. Tension is going towards the center of the circle, that's radially inward. Gravity is going away from the center of the circle, so that's radially outward. And so both Ft and FG, both of those contribute to the centripetal force. And now I write down my second law equation, Fc equals mv squared over r. I start the same way as I did before. I know the mass is 0.2. I know v squared is unknown. I know the radius is 0.5. And then on the left side, I write down the sum of the forces before I plug in any numbers. Now remember, by convention, towards the center of the circle is always taken to be the positive direction. So I'm going to write down Ft minus Fg. Fg I can calculate because I know Fg equals mg. That would be 0.2 times -10. That would be -2 newtons. By the way, that negative sign I've already taken into account here. So don't like double put the negative sign. I'm not going to like subtract -2. There should be a -2 right here. So Ft is 5 minus Fg, which was 2. And so now notice my answer is going to be slightly different than it was before, because now I have 3 equals 0.2 v squared over 0.5. And so now if you multiply and divide and take the square root, let's see what we get. 3 times 0.5 divided by 0.2, take the square root, blah, blah, blah. I get now 2.74 meters per second. And that is the answer for example 2. Now I do want to point something out just to show you something. Let's say I had written at the top of the circle, not the bottom of the circle, the tension is 5 newtons. Okay, I want to show you how that changes things. Okay, so make sure you add this to your notes right now, and then I'm going to adjust things slightly. Okay, so what if it had been at the top of the circle? What if I said the tension at the top of the circle is 5 newtons? How would that have changed things? Okay, so here's what would be different in that situation. If it's a vertical circle, at the top of the circle, the picture is slightly different. So now here's the string, here's the ball, it's going around in a circle, blah, 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 whatever. But now when I draw the FBD, tension is going down because it's going towards the person's hand. But now the force of gravity is also going down. Okay, so FT and FG are now in the same direction, and they're both going towards the center of the circle. Okay, which means you take both of those forces to be positive. So at the top of the circle, instead of Ft minus Fg, it's actually going to be Ft plus Fg. Okay, and so what would that change? That would just change the calculation slightly. Okay, because then that would be 5 plus 2, which means this would be 7 instead of 3. And then if you made that change, you would find V is equal to, let's see, 7 times 0.5 divided by 0.2 square root, blah, blah, blah. I get 4.18 meters per second. So whether it's at the top of the circle or at the bottom of the circle changes how you write down the sum of the forces because it changes which forces are going towards the center and which ones are going away from the center. Okay, so in the next video, we will finish up talking about centripetal force and we'll do some more complicated examples. And then we will be done with the second third of this unit. As always, please let me know if you have any questions, and I'll see you guys in the next video.